Just continue? Yep. Okay, cool. So yeah, scoping. So in most languages, you have public-private to indicate the scope or visibility of your function, but in Go, it works off a principle of uppercase and lowercase. So lowercase means that it's private, uppercase means that it's public. And this is a very, very, it seems, it's a very simple convention, but it actually works very, very well when you're writing and programming in Go. So that's how you do scoping in Go. There's no protected scope in Go. There's only public-private. Object orientation. So
can I ask a question?
yeah, go for it.
If you extend the class, how do you, so you cannot extend and have the method only in the subclass. You have it public or you don't have it at all.
Yeah. So we'll get into object orientation now, and you'll see that it's different. Yeah, it's quite different. Yeah. So, okay. So Go has no class type. It only has a struct type, and structs basically represent data, like in most languages. And this is just how you declare a struct type. It's type bar, for example, of type struct, and then we associate a method with the struct. So it's just an association. And this is basically the same for an interface type. Again, this is the signature that the interface expects. So if we just move on to the next slide. So this is, Go doesn't have an inheritance model, it has composition. So this, I guess, answers your question. And you can see here that we've got two structs, and they've got name properties. And we've got a book which is composed of author and publisher. And then it also has its own title prop. So there's no overriding of, there's no inheriting methods and stuff like that. You simply compose stuff together. So here we have taking our example a little bit further, where we've got a getDetails method, which is inherited from book. Which is associated with the book struct. And we're simply just going to return a string, which takes the title. And also we've got title, we've got the publisher.name. So we're using b.author, so we're taking this one, and the name, which comes from here, and then again, the same for publisher. Now, because it's composed, you don't have to. You could just go b. If this was called author name and publisher name, you could go b. author name, b. publisher name. But because they've got the same name, there's an ambiguity. So we have to resolve that by accessing the composed objects directly. So interfaces are explicit. So what that means is a struct does not implement an interface directly. It's more the compiler will check at compile time whether you are passing an object that satisfies the interface that the object expects. So here we go. So here we have a log handler interface, and that has a write function. We have our struct, which expecting a logger of that type interface, supporting that interface. And we have our bar function here, which is associated with the foo struct, and that will simply write bar to the log. And if we go on to the next slide, we have our loggers package, and we have a console logger. Yeah, and it doesn't implement the interface directly, but it has the same signature. So it has the write method, which takes a string, which matches that interface there. So write with a string. And then we can simply use that logger. We can pass that into it. When we initialize our struct, we can pass that logger in like that. And when we call bar, it will write bar to the logger. So it's pretty simple. And what this allows us to do is it means we can create very very specific objects which can implement very specific interfaces. well, which require very specific interfaces, and it just limits our scope. So we're not pulling in a whole lot of methods on an interface that we don't need. Yeah, so we can have a struct which takes a very specific interface, and we may have an object that has those functions on it, but may have other functions, but the object that we're passing into doesn't need to be concerned about those. So that's, yeah, so I found that to be pretty good. I'm just going to jump just quickly into testing before I jump back into actual implementation stuff. So testing in Go. So it's Go comes with a built-in sort of testing framework, and this is just how you set up a test. So we've got again your package. We're going to import the testing dependency here, and we're going to set up our test method. So always start with the word test, and then bar is the function you're going to test. And we're going to call it, and we're just going to check if what we expected is, and if we don't get what we expect, we're going to print an error. By convention, you'll find that Go has certain conventions. One of the conventions is that it must be underscore test. .go must be the name of the file, and then when you run go test with this, it'll find all those files and execute them and give you back some feedback. We can also test private methods. So private means that private is any method that's private is only private to the outside the package. So you could have many files with the same package name, and they'll all be able to see the private methods. But outside of that, they can only see the public methods. So another package using one package that has private methods, it'll only see its public methods. Yeah. So for example, we have the math package, and we have this calculator struct, and we have an add method on it, which is lowercase, so it's private. And then we have our testing, again, same package name, so we can see it, and we can use it. And then we can just write a test against it, like that. So this is just some screenshots from Visual Studio Code. I found Visual Studio Code has very good support for Go. So as soon as I created my first Go file, it prompted me to install a whole bunch of packages and stuff. So I did that, and then I got great support from the IDE. So we can see here for an individual test method, we can click on run test, debug test, or we can run all the tests for the package. And we've got highlighting here. So this is a test that I ran, and you can see that this is in red. So the test, I didn't have coverage for this. So I thought that was a pretty cool feature. I've seen that in JavaScript, but I haven't been able to get it to work, but it worked really well in Go. Okay, so we'll jump back. It's enough on testing. So concurrency. Okay, so concurrency, as I said before, is something that Go is probably more known for. And it has so Go is a concurrent language, not a parallel language. Does anyone know the difference between concurrency and parallel? Okay, so concurrent means that it schedules. Parallel means that things run at the same time. And concurrency means that things are scheduled and run a little bit of this, run a bit of that, run a bit of that, like that. Yeah, so that's how Go operates. So it has a very efficient scheduler in it, and each Go routine runs on it has a single thread for a group of Go routines. So threads can be very expensive. So you can schedule multiple Go routines on a single thread. And it will create as many threads as it needs, and it puts all the Go routines across them. It's in a nutshell how it works. So a Go routine is just, you just declare it as normal function, and then you put the keyword Go behind it there, and yeah, it becomes a Go routine. The main function is, as I understand it, is also a Go routine. So that means that this will run concurrently from the main Go routine. So channels and queues, and there'll be more examples of Go routines and stuff coming up. So in order to communicate between, if you want to pass data between Go routines, use a mechanism called channels. So there are two types of channels. There's buffered channels and unbuffered channels. From what I could tell, buffered channel, an unbuffered channel is like it's the same as a buffered channel, but it has a size of 1. So a buffered channel, you specify size, so let's say 5 items, and that means you can write 5 items to it before it blocks. And you can read off 5 items before it will block. So it'll block when it's full, and it'll block when it's empty. Unbuffered one, you don't give a size. As soon as you put something in it, it'll block immediately. And as soon as you try to read, the next time it'll block. So it's like it's a buffered one with a size of 1. There's also directional, so you can say that the channel is read only or write only. And we'll see later why that's useful. But by default, read only. Sorry, 2 ways. You can read and write. So here's an example of a unbuffered channel and how we're going to use it. So we use the make function and we use the keyword chan. And this is just a struct. I haven't put it here, but just imagine that it's just a struct. It's like a type, like an int or a string or whatever. That we're going to say our channel supports, our channel is of this type. And we call it go routine, go process, and we pass in our channel, which is here. This is our function, and it's going to take a channel of type job, and this is how we loop through channels. So this will keep looping until it runs out of channels, and then it will block. Anyway, but it will sleep. Yeah, for each one it will sleep. And then here we're pushing each job onto each channel, and the arrow indicates whether we're writing to a channel or reading. So if the arrow was on this side pointing to the job, that means we're going to read from it, and this is because it's that way. We're going to write to it. Sorry, to the channel, and then we'll just print done at the end. So buffered channels, it's again the same setup, but we're giving it a size. Oh, just one more thing. What will happen here is when we write the first one, it'll block here, and then this one will pick it up and sleep 10 seconds. So after 10 seconds done, it will go around again, and so when it reads it, that'll free up that, and it'll write it, block, but this is sleeping 10 seconds. So we're blocked here, and it'll loop again. And once this is up, it'll loop again and then read it, and then we're freed up, and then it'll read this one again, and it'll block, and so on and so on and so on, like that. So that's unbuffered channels. It's going to block on each one. So buffered channels, again, yeah, okay, given the size of 5, it means we can write 5 items before it will block. So we'll just write all of these, and then we'll run our go process, and we're not going to block on any of these, and it will just loop through them, just sleeping, and then this will actually exit because this is go routine. This example will actually exit before this is done, but yeah, just you get it as an example. Yeah. Okay. So one-way channels. So one-way channels, the only thing I could find that was useful about them is if you got a channel and you want to pass it to a function, but you want to have some control over how that function is going to use the channel. So you might want to say, I'm going to give it a channel with a list of items, but you don't want it to add more. You just want to read from it, so you can make it a read channel, and you do that by pointing the arrow. So in this case, this is pointing away from the job channel, so it's a read channel. If it was pointing the other way, it'll be a write channel. So yeah, a write channel again, if you want to process some jobs or some items, and you want to give it to a function that will populate it, you may just want to give it a write channel. So that's really the only thing I could really find useful about one-way channels. Maybe there are some other uses for it. So closing a channel. So we can use a close built-in function here, and that means that's just signaling to the runtime that we're done. We're not going to do anything more with this channel. And so here you go. So we're starting our make a channel, we start a go routine, we add a couple of jobs to it, and then we close it. And that will cause this to loop. And it won't block when it runs out of, so when it's normally what will happen is when it's empty, because it's a buffered channel, it will normally block, waiting for more items. But because it's got close in it, it will see the close, and after it's processed 2, it will simply exit. And that will be the end of that. So close is just signaling that we're not going to use the channel anymore, so we're just going to exit there. Deadlocks. So Go has great concurrency support, but we need to be aware of deadlocks. Deadlocks work if a Go routine basically if the program can't continue, that will result in a deadlock. So this is a unbuffered channel. This is an unbuffered channel because we haven't got a size on it, but I'll just skip back. I just want to show you there's a bit of a difference on our first unbuffered. So see how we've got process Go first before we add jobs to it. Okay, and in the next, in the deadlock example, we've got it last. The reason we need it first is with unbuffered is because unbuffered channels will block immediately. So in here we'll try to write and we'll block, but we haven't kicked off the Go routine because it's down here. So it will deadlock here, and you'll get the runtime will panic and exit. And we'll look at panics in a bit. But this is an example of a deadlock. Any questions so far? No? Bit much taken? All right. So select. So a select is, think about it as a switch case statement, but this is for Go routines, and it allows you to automatically distribute work between Go routines, and we'll see how that works. So here we go. We have a worker function, and we're going to create 2 channels, and we're going to kick off 2 worker functions, one for each channel, and I've just got a time in there just to create a bit of a difference between them. So this one will sleep for 2 seconds, and this one will sleep for 10 seconds between each job. And then we've got a loop. And what this will do is it will push count onto a channel, and that will cause the Go routine to pick it up and process it and then sleep. So the first iteration, both channels are available, so it'll just randomly pick one. Okay, so let's say it picks B. And that'll go there, and it will sleep for 10 seconds. So the next iteration will go, B is busy, okay, I'm going to put it onto A. And then that'll sleep for 2 seconds. Next one, it will go along, none are available, so it will wait. And once the 2 seconds are up, in this case, it'll push it onto A again, and A will work. So you can sort of see every 2 seconds we start off pushing onto B, then we push it onto A because the next available, then 2 seconds A again, 3, 4, 5. Then B has finished its 10-second wait, so it's freed up. So the next one will go onto B, and then we're going back onto A again. And that's just how you can distribute work. And another example is maybe you've got like a web service or something, and you've got a couple of web services, and you just want to distribute some work between them. This is one way you could do it. Shared resources. So channels is one way to share data between Go routines, but let's say you've got like a global variable. I'm just going to use an example of count that you want to increment. You want 2 Go routines to increment it. How do you synchronize? So mutexes is a very simple method of doing it. Mutex is a lock primitive. And we can just use this to synchronize reading, writing a shared resource. And we'll have a look at mutexes. So here we go. If we just import our sync package. I'm just going to set up a global variable here, and I've got a mutex. So I'm just going to set up my mutex. I'm going to pass my mutex into my function, and we're going to lock. And so what this means that when I'm looping here, I'm going to create lots of Go routines, and each one will wait. So the first one will come in, there's no lock, so it'll lock it, increment, another one come in, and it's locked by the first one, so it's going to wait, and then this one will update the counter, unlock, and exit, and the next one will say, okay, I'm unlocked, and I'm going to update the counter. The next one, wait for that, and so on. So that's just a very simple way to set up some sort of control around the shared resource. You can use channels to do this, but this is a simple way if you just want to protect the shared resource. Error handling. There are no try excepts in Go. There is sort of a concept of finally. It looks like finally to me, but for error handling, try except style, we've got multi-return values in Go. So you can return an integer, an error. You can return other parameters as well, but this is just the example of errors, yeah? So here we go. We've got our calculate tax function, tax rate. So let's say get tax rate returns an error. We're going to check for the error, and we're going to return 0 and error. And the caller of this function will again check for error. If it's got an error, it's just going to ignore that value, and it's going to do whatever it wants to do based on the error. If there's no error, then we're going to return nil as the error and the amount. So the caller will check, okay, I've got error of nil. I can then process the amount of the tax amount that's come back from this. So that's error handling. Panic. So I mentioned earlier that if you got deadlock, the system will panic. A panic is something that you would use when the system cannot recover from the error. So a simple example is configuration file. So maybe it needs a configuration file and it's not available, so it will panic and you can't recover from that. So this will cause the application to terminate. So as I said before, defer is like a finally. So here we go, we've got a connection string. Oh, sorry, we're setting up a connection. We're going to check if there's an error. And if there's not, then we're going to defer the close. And then we're going to do some query. When this exits, it will run the defer and close the connection. So it can be like considered like a using clause in C++, C#, sorry. Or a finally or something like that. It's a defer. And you can defer lots of things, not just one. You can put other defers within your same function. And I think they get added to a queue and then processed after the function exits. And they are guaranteed to run even in the case of a panic. Recover. So let's say we've got to recover. So let's say we're panicked on something, but we want to recover from it. So in this case, we've got our main Go routine, and it's calling some function here, which calls another function, which was panics. So we have to defer a recover. So when this exits, it'll run the recover, and then we'll be saved. So this will still print. Yeah. So the application won't terminate. If we don't have the recover, it will end, and you won't get this. So you can only recover from inside a panicking Go routine, not from the outside. So in this case, we're trying to recover here. I'm not sure why I've got it there, but anyway. If we only had the defer here and our Go routine panicked, then the program will still terminate. We have to actually have the recovery within. No, that's wrong. That shouldn't be there. Okay. Anyway, in any case, yeah, that's right. I refactored this last night. In any case, this won't work because we have to recover inside the Go routine. So it will just terminate. Yeah. Let's look at the next example. Okay, recovery must be inside the packet. Yeah, okay. So you can see here we've got our Go routine and we've got a defer recovery. So when this panics, it'll exit and run the defer, and then we'll be saved. And it'll do the sleep, print the time. So defer only works within the Go routine, not outside. So that's it. Any more questions at the moment? No? Okay, cool. Arrays, slices, and maps. So, okay. So the basic I guess the basic thing in basic type of, I guess, list or in Go is an array. And there's just different ways to declare them. They have to have a fixed size, so you specify the size and you can add some items to it, or you can give a size and put some items like this. Or you don't have to put a size, but you have to put your items and it'll just work out the size. And you cannot be changed after that. So once you've done that, that's it. You can't add, you can't remove, that's your array. Then you've got slices. So a slice is a slice of an array. And you can see here we've got our array foo from up here, and we're going to slice it at position 1 and up to 2. So we'll get B and C. And we can use this built-in function here called append to add more to the slice. So we can take our slice and we can add more to it. If we want to remove from the slice, we have to slice it again. So an array is, sorry, a slice is just a pointer to an underlying array, and when you use this, Go does some stuff underneath to adjust our array. But yeah, if you want to delete, you have to reslice it again. Slice to slice. That's how it works.
So as soon as you go back.
Yep.
So as soon as you slice it.
Yep.
You can add or remove, but it's just a normal array. You defining you cannot add or remove.
Yeah, basically. Slice you can add to it, but if you want to remove from it, you have to slice it again. Yeah, there's no remove. Yeah. Maps. So maps they're a bit slower, but they give you full control. So you can create a map like this, or you can use the make. I don't know what the difference is. It's just two ways of doing it. And we can then add to it, or we can delete from it like this. So we can say which item we wanna delete using the delete keyword. So just more control over it, but it's slower. Just going back. So arrays are value types, and slices are also reference types, and this is important because of how they're passed. So when we pass an array, when we're passing a value type, we're passing a copy, and when we're passing a reference, we're passing it's just a pointer, which is interesting because in certain languages, I think C++, passing by value can be slow, so people pass by reference. But in Go, what I've read, it's the opposite's true. So Go is more efficient for passing values, but I think it really depends. But yeah, generally, passing by value is faster. So these are maps and reference types. Oh, the other thing about value types and reference types are reference types. When you pass them a function, if that function modifies it, it will be reflected in the caller. Value types is a copy, so yeah, it's immutable. And this is how we iterate arrays. So either we can just use a standard for loop, we can use a range. Underscore means that we're just ignoring this, so this actually has 2 parameters, but we're just going to ignore that one. And this underscore is useful as well for things like errors, like if you're doing like a unit test, but you want to ignore the error, you can just put an underscore in front of the error, and your next unit test may test the error and ignore the first value. So that's what that is, and we can just loop on the range. Maps is a little bit different, so we have a key value, and when we loop, it'll extract the key and value, and then we can act on them within our loop. Otherwise, you can just get the key if you just wanted the key. Pointers. So yeah, I sort of already covered this, okay, so again, here we've got our foo struct, and we've got a function which takes a pointer to foo, and then we can use this one to create a reference and pass that in. So we can then modify foo in this, and it will reflect out here. And this is useful. Okay, I'll get into why it's useful down here. But this is just if we're going to dereference it. Star on the other side dereferences and gives us back our value and underlying struct or value or whatever. But we don't have to. We can just do it like this, and the compiler will figure it out. It'll take care of it for us. This is an example. So let's say you've got a struct with some data in it, and it's got some functions associated with it, and when you call the function, you want it to change the data in your struct, yeah? So that's why we can use a pointer type here, and then so when we create a new instance of foo, and we call modify foo, so foo.modify foo, it will change it. It'll change the object that we've told it to act on. That's one use for those.
And if you don't put star,
Yeah, if you don't put star, yes, you'll get a copy, and you'll be wondering why my structure is not changing, why the data is not changing, because actually a copy is passed in. Yeah. So routing, so I think we're pretty much at the end now. So routing, look, it's a server-side language, so routing is something you probably want to do. And these are just different libraries of routing. This is the basic one that comes with Go. This is a very fast one. I'm using this one at the moment. It's very, very simple, but it's very good. You'll notice that a lot of these routing libraries, they more showcase their performance than their features. So if you go into GitHub, they've got lots of benchmarks about how they're faster than some other router, or even in other faster than other languages, or faster than other routing packages in Go. That's something I noticed. This is another popular router. It's probably much more feature-rich than this one, but it's slower. But it's still reasonably lightweight. And then you got your MVC frameworks here, like Iris Echo. I use this one. This one's pretty nice. It's got lots and lots of features. I haven't used this one before, but this is another popular one. And if you want to do webhooks, then Gorilla webhooks is what everyone seems to be using. So what can we use Go for? Microservices, AWS Lambda. So AWS recently announced they support Go. You can serve React, so I'm doing that with the HTTP router, serving my React app from my Go service, which also has an API on it. Mobile, so they're getting into the mobile area now. So it does play well with React, and there's quite a few, there's a few tutorials on how to do it. It's pretty easy. I haven't actually done it before, but I've read through the tutorials. And yeah, it's just useful if you just want to have a single code base between your front end and your back end. Or you want to do something, you got some, you want more performance in your mobile app. You can just Go and run React for the front end, for the UI. And there's some resources. Yeah, just links, resources to popular stuff for Go. And that's about it. Cool. That's it. Any questions?
So what was your reason for using Go in that application that you needed to build?
So I wanted, well, one reason it was just an excuse to use a new language. Yeah. But it was kind of, I found it kind of slow, and I thought, well, if I use Go, maybe I'll get some more performance out of it.
Did that happen?
No, it was, yeah, 'cause it's a pretty simple service. But in terms of performance, I think it was pretty much the same. And I think actually my issue might be how I've done my front end, maybe. But yeah, mostly it was just an excuse to use another language. Oh, yeah, no, actually, no, there was a very good reason. It was the single executable. I didn't want to. So I didn't want to have to, install all the packages and stuff. I just wanted a single executable I can put in there. Put onto my server, and it will just work. Yeah, I also read that you can build like resources such as web pages, static web pages into your executable, and you can serve them straight from the executable. So you can have a single executable with everything in it. Yeah, I don't do that, but apparently you can do that. Yeah. Cool. I just found the error handling, a bit cumbersome a little bit, but I try to keep the functions very short, so only one if error. What else? I got a little bit confused at the beginning about the interfaces. I sort of had lots and lots of interfaces, and I wasn't really sure how to use them properly. But yeah, I think I've sort of got it down now. Just yeah. But otherwise, no, not really. It only took me like a few hours to learn it, and then I was rewriting my service, and that includes the tests and everything. Yeah, I wasn't like the accessing the file system. So my service has access to the underlying file system, and I wasn't really sure how to mock that. Yeah, but there are tutorials. I found some tutorials later on how to mock it for my tests. Yeah. Bit of a learning curve with the routers and that. Yeah, I started off with Iris, but my executable became like 20 meg, which to me seemed a little bit big, and so I switched to the HTTP router, and then it was around 5-6 meg. Whether that's really a concern, I'm not sure, but yeah, cool. All right, thanks guys. Thanks.